For your information, every ChatGPT response starts with this calculation. You'll find out that calculation in this video. Okay, so every ChatGPT response starts with this calculation, and well, straight up, here you learn about token probabilities, prediction pipelines, and large language model text generation. And the objectives are as follows. You'll be able to explain why every LLM response begins with probability estimation, understand what tokens are and why LLMs predict tokens instead of words, describe how logits become probabilities, explain the role of softmax, understand the prediction pipeline used by transformer models, then implement simplified prediction algorithms in Python, and explain how decoding strategies affect generated text. Let's go. So the central idea is that every response generated by ChatGPT begins with the same mathematical question. And the question is simple. Given all previous tokens, what is the probability of every possible next token? Given that we already have this particular thing in place, what is the probability that we are going to have the other ones following? So the model does not generate an entire sentence at once. And that's why we talk about the idea of tokens, as you have seen in previous videos. If you have seen other videos, the videos before now, by the way. Now, instead, it repeatedly performs this cycle. First of all, it reads all previous tokens, then it predicts probabilities for every possible next token, and it selects one token, it appends it, that means it adds it to the already already uh appended tokens, then repeats until the response is then complete. So this simple process produces essays, code, conversations, and stories. So when you prompt generative AI, this is exactly what is happening. So now why this is called next token prediction, right? Suppose the prompt you give to ChatGPT or any other AI, generative AI for that matter, is the earth revolves around that's the prompt. So the language model predicts the probability of every possible next token. So the earth revolves around the sun, the moon, the galaxy, the banana, the computer. So and then probabilities are assigned to each of these words. So for instance, the sun has a probability of 0.95. That's really high, and others are, you have the moon, which is not so close, but at least it's the closest. Then you have galaxy, which is a bit close, but not as close. Uh, Closer than banana and computer, for instance. So you see that the highest probability token is the sun. Then the response becomes the earth revolves around the sun. So the entire prediction process then starts again if you get to prompt something else. So now the next question I want to see is they talk about tokens. I've been talking about tokens from some of the earlier videos in this playlist. So humans think in words, right? Humans think in words, but language models think in tokens. In essence, humans understand language. So that's why we talk about languages, right? But the language of computer is numbers. So lang words are to human what numbers are to language. And in the case of generative AI, the first step in the process of converting words to numbers is first is it starts with tokens, in short. So a token can be a word, it can be part of a word, it can be a punctuation, it can be numbers, it can be spaces, or even emojis, right? Example, imagine this sentence. Artificial intelligence is amazing. That's the sentence. Then you can then tokenize it into the following token. So the possible tokenization can then be artificial as one token, then the space, then intelligence. So the space together with intelligence is another token. Then the space and is, you can say artificial, that's one token. Then the space here and intelligence is another token. The space and is another token. Then the space and amazing is another token. And then full stop is another token. So we have broken this one sentence into one, two, three, four, five tokens, right? Sometimes it may even go further to say maybe arti. Arti is one token, facial is another token. So it depends on the model you're using. So another example is unbelievable. So imagine you have unbelievable, and that may become on, that's one token, believe, that's another token, and then able is another token. So the model predicts tokens, not complete words. So because computers do not understand human language, right? They convert our words into tokens, and then we see other things. So every language model has a fixed vocabulary. So example vocabulary can be things like cat, dog, fish, bird, computer, banana, and the real language models typically contain 50,000, 100,000, or even more than 200,000 possible tokens. So for every prediction step, then the model computes a probability for every token in this vocabulary. So there's a probability for every token in the vocabulary. So imagine the concept of token probabilities now. Suppose the vocabulary contains cat, dog, fish, and bird. And then the model you have, okay, I think this can be better. Let me make this better using dollar signs now. This can be okay. So now imagine that you have the you have a vocabulary that contains cat, dog, fish, and bird. Then the model predicts cat 0.4, dog 0.3, fish 0.2, and bird 0.10. Then you can then notice that if you add it all up, you get one. So the probabilities always sum up to one. So at every stage of the token probabilities, you have everything summing up to one, as which is one of the key things about probabilities. So now the next question is, where do these probabilities come from? That's the question to ask next. The neural network does not directly produce probabilities for sure. Instead, it first produces values called logits. Logits. So for instance, maybe for cat, the logit is 5.2. For dog, the logit is 4.8. Fish, the logit is 2.1. For bird, the logit is 1.0. And then the logits may be positive, they may be negative, they do not sum to one. They do not, logits don't have to sum to one like probabilities. And they are not probabilities, of course. So they must be, but then these logits are converted into probabilities. So, and then that brings up the idea of softmax. Now, it is softmax now that converts logits into probabilities. So imagine the softmax equation, which is this: pi equals exponent zi over summation over j of e raised power zj. So that simply means, okay, I think I can make this better too, with single dollar signs. With single dollar signs. Then here to have dollar and dollar. I hope that's all. Yeah. That's all the equations. So you see, Zi now is the logit. So this Zi is the logit. So all these logits you have here, all the 4.5.2, 4.6, and the rest, they are the logits. And then E is the Euler's number. That's 2.718 and all that. So the denominator ensures that every probability is positive and all probabilities sum to one. So this softmax equation now converts the logits into probabilities. And we're going to see that in a jiffy. So imagine that you have softmax here. Example of softmax. So suppose the logit of a particular token A is 2, the logit of B is 1, and the logit of C is 0. So you compute the exponentials, right? So these exponentials are like the exponentials now. So if you compute the exponentials, you have e raised power 2, which is 7.389. You have e raised power 1, which is 2.718, and e raised power 0, which is 1. And in step 2 now, you then compute the total. So the total of all that's 7.389 plus 2.718 plus 1, and that's 11.107. In step 3, you then normalize the probability, you normalize the exponents to get the probability. So for instance, A now would now be 7.389 divided by the total. That's what this formula is saying here. So this, you take the exponent of it, right? So you pick that first one, 7.389 all over 11.107, you get 0.665. Then B, 2.718 over 11.107, you get 0.245. C, you have 1 over 11.107, you get 0.090. So these values now form a valid probability distribution like that. So you can of course do that using a simple Python code like this. So you import number as NP. So you declare the logits as an array in a list 210. Then you take the exponent, that's exponents of the logits, and then you take the probabilities now, which is each exponent over the exponents, the sum of all the exponents, like that. So you then print the probabilities and you have the answers just like what you have here. You have them here. So of course, the coding now is important for when you have large, you have like 50,000, 100,000 tokens like that. So we then have the prediction pipeline. So every generated token passes through the following pipeline. You input your text, that's whatever prompt you put in. Then your prompt is tokenized, and then you have embeddings. Then so the embeddings now is the process of converting your tokens, of assigning vector numbers to your tokens. And then these are processed by transformer layers. And then you have final hidden states and you have some linear layers. Then that leads to the logits, and the logits leads to the softmax. And the softmax leads to the token probabilities. And then you have your sampling strategy. And then from the sampling strategy, you then take your next token, which is probably the token with the highest, which is most likely the token with the highest probability. So the entire pipeline repeats once for every generated token. So imagine when you if when you give it just a one sentence prompt and you get like 500 words at the same time. So this is the calculation that is happening over and over again for until you get as those words are coming out. So you see the words comes out sequentially because you have that calculation happen very fast. So prediction example now. So imagine you prompt the capital of France is blah blah. So suppose the model produces London, Paris, Berlin, and Rome, and London has a logit of 1, Paris has a logit of 6, Berlin has a logit of 2, and Rome has a logit of 1. And then the softmax probabilities will now be something like so for Paris now you have 6 over the total. That's 6 over the total is actually 10, right? 6 over 10. Okay, softmax, you do the exponent of 1, exponent of 6, and all that. And then you divide by the total. So Paris produces 0.986, Berlin produces 0.07, London produces 0.06, and Rome is 0.001. So the model then predicts Paris because it has the highest probability. So so the prompt then becomes that the capital of France is Paris. So the prediction process begins again if you have any other request. So this is exactly what is happening in that place. So you have 9692 here. Yeah, so okay, this one says 986. But I think this one can be better relied on. Yeah, so it's better to rely on this one. So this is 9692 here. So you have the logits, you take the exponents, and then you do the whole probability over sum of the probability, and then you get for London 0.065, Paris 0.9692, Berlin 0.178. So Paris, of course, has the highest probability, and then that is your response right there. Now the question is, why does generation why generation is iterative? Why is generation iterative? Question. So suppose the model has already generated the capital of France is Paris. Now it predicts the next token. So possible probabilities can be full stop probability 0.70 and 0.12, comma 0.10, which 0.08. And suppose it selects full stop because the size probability is 0.70. Now the sentence becomes the capital of France rather is Paris, full stop. Okay, so that's what comes. Then the prediction cycle repeats. So one token at a time. So you see that same calculation happens over and over and over again until you get your complete result. So now let's talk about greedy decoding. The simplest decoding strategy is greedy decoding. And the rule is you always choose the token with the highest probability. That is greedy decoding. So it's more like you have three job offers. You just simply pick the highest paying one. Of course, that is not as humans, right? We don't always make such decisions. So you may even end up picking the least paying job because you want to be close to family or something like that. But in the case of AI, right? The the simplest strategy is greedy decoding, and the rule is you always choose the token with the highest probability. So it means that if you have tokens ABC with probability 0.80, 0.15, and 0.05, the prediction will automatically be A because that's the highest probability. The advantages of greedy decoding include the fact that they are fast and they are deterministic, so you know for sure what you're picking. The disadvantages is that they can produce repetitive text. So they can produce repetitive text, and that's why AI can make mistakes. So all the AI they tell you that you can there's a possibility that there can be mistakes like that. So it can produce repetitive text. So imagine this is a possible case now. You have this probability of 0.80 and all that, and then the prediction. So if you calculate the argmax of the probability, it can end up being 0, right? You can have repetitive text like that. Then talking about random sampling now. So instead of always choosing the highest probability, we may randomly sample according to the probability distribution. Example, you have cat to be 0.6, dog is 0.3, and fish is 0.10. The possible outputs can be cat, cat, dog, cat, fish, cat, like that. So we have that kind of random sampling. In that case, the higher probability tokens then appear more frequently, but lower probability tokens may also be selected. So here now you're giving yourself the chance. It may be possible that the token with the highest probability is not necessarily the desired result. So that's why random sampling can work compared to greedy decoding, where you just pick the one with the highest probability. So imagine this now. So import number as NP. So you have tokens cat, dog, and fish, and probabilities are 0.6, 0.3, 0.1, like we have up here. And then for every item in the range now, in the range from 0 to 10. So you want to bring this up in a range from 0 to 10 randomly. So you print np.random, then the choice of tokens with based on the probability. So that's why you have dog coming first. You have cat, 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 because cat has the highest token probability. You have fish, dog, and cat, 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 like that. So there's a higher chance of picking cat, but there's also some chance of picking other ones too, and as opposed to greedy decoding. Then we talk about temperature. I think I've talked about temperature in one of the earliest videos too. And I think there's still a video as we go on this playlist that talks basically about temperature. So, and when we talk about temperature, it's not the temperature like we know, a temperature that is connected to climate or weather. So, temperature controls how confident the model becomes before sampling. So, the logits are divided by temperature before applying softmax. So, for instance, you have Pi, that's your token probability now, is the softmax of Zi over the temperature. So interpretation is this. The low temperature means more confident predictions, and high temperature means more diverse predictions. So if you are looking for confidence, you go for low temperature. If you're looking for diversity, you go for high temperature. So imagine original probabilities now, token A, B, and C with probability 0.7, 0.2, 0.1. So the approximate effect can now be this now. So with a temperature of 0.5, A has probability 0.91, B has probability 0.07, and C has probability 0.02. With at a temperature of 1.0, A has probability 0.7, B 0.2, C 0.10. And at temperature of 2.0, A has probability of 0.52 and B has 0.28 and 0.20. And in line with what we said before, low temperature of 0.5. So here you can easily decide for A because you can make confident predictions there. But when the temperature is high, like 2, so you have things even a bit more evenly distributed. So you see B and C are really close compared to when the temperature is 1 or even 0.5. So that's the idea of temperature. So imagine here you have an array 3 to 1 at temperature 0.5. Now you have the logit over temperature, and then you take the exponent and all that, and you get 0.866 and all that. So at a low temperature, it's easy to decide to know the one with the highest probability. But imagine you now raise the temperature to say 5, so everything is becomes a little bit more closely distributed, as you can see here. Okay, let me try 50. I don't know if that makes sense, but I'll just try. Okay, so you see everything is almost like the same. So if I say 500, it can hardly, I mean, everything has almost the same chance of being selected. So if you want if you want confident prediction, you go for lower temperature. If you want diverse prediction, you go for high temperature, like we've talked about, like we've said already. Then we have top K sampling. So top K sampling keeps only the K highest probability tokens. So here we are talking about the possible sampling. We've talked about greedy decoding, random sampling, and then top K sampling. Now top K sampling keeps only the K highest probability tokens. For instance, you have A to be 0.5, B is 0.20, C is 0.15, D is 0.10, and E is 0.05. So if you have K equals 3, then it means you are picking the top three. So you want the top three predictions now. So in this case now only A, B, and C will remain. So the probabilities are then renormalized before sampling. So as you've picked A, B, and C now, they now renormalize probability by taking the total and now saying 0.5 over total, 0.2 over total, 0.5 over total, and then you now use that to make your prediction. Imagine this now. So you have 210 as the top probabilities. Of course, it's not directly connected to this, but imagine that the top K, your K is 3. Okay, imagine the probabilities you have 0.5, 0.2, 0.15, 0.10, 0.05. So I want the top three. So for the top three now, so you then have 210. That's the biggest probability here is this is 0, 1, 2. Yeah, you just have the top ones are these three now. Then you now renormalize and you have 0.176, 0.23 and 0.588 and all of that. So that you have that normal renormalization. That's for top K sampling. Then for top P or nucleus sampling, what will happen here is that top P sampling select the smallest set of tokens whose cumulative probability reaches a threshold. For instance, if you want a threshold of 0.9, you just state it. So it means that the cumulative, anyone that has a cumulative probability of 0.9 upwards, you pick. So for instance, you have A, probability 0.5, B, probability 0.25, C, probability 0.15, D, probability 0.007, E, probability 0.03. Then the cumulative, of course, 0.5 plus 0.25, you have 0.75 plus 1.5 plus 0.15, there's 0.9 plus this, you have 0.97 plus this, you have 1.00. So for probability equals 0.90 now. For P equals, so top P sampling select the smallest set of tokens whose cumulative probability reaches a threshold. So here now, so you pick the threshold you want is 0.9. So after 0.9, you have a cutoff. So it means here A, B, and C fall in place. So then A, B, and C are kept because they all reached. So it is A, B, and C that accumulates up to 0.9. So you keep A, B, and C. So the remaining tokens are discarded before you now sample. So in summary, we see that every ChatGPT response begins with the same repeated computation, which involves converting text into tokens. So converting human language, that your prompt in human language converted into tokens, and the tokens are encoded as vectors. I mean, we've talked about this in previous videos. Then the process then you then process these vectors using transformer layers. Then you produce logits for every vocabulary token. You apply softmax to obtain probabilities. Then you select the next token using a decoding strategy. So it can be greedy decoding, random sampling, top K sampling, top P sampling, and all of that. Then you can append the token to the prompt and repeat until an end of sequence token or stopping condition is reached. So this repeated non-token next token probability prediction is the fundamental calculation under modern large language models. So every ChatGPT prediction starts with this kind of thing, next token probability prediction. So it's more like each result you get, you have many probabilities being computed and decisions being made very fast for you to have all those things as they come out sequentially. So yeah, we have our practice problems, and as usual, I get to solve two of them. So in this case, I'll be solving 7 and 15. Answer the following questions without referring to the worked examples, unless stated otherwise. Explain your reasoning and show intermediate steps. Okay, I guess I want to put the 3 marks under this to produce that long line that divides. Yeah, so something like this. So example, so you have one now. Okay, let me just flash them. You have explain why a language model predicts the next token instead of generating an entire sentence at once. Of course, we explained that. So you have 1 to 5 showing, and then 6 to, can we say up to 6 to 10? So I'll be dealing with 7. Compute the softmax probabilities for the logits and give you answers to 4 decimal places. We're going to be doing that. Then, of course, just like we'll do this, you can handle this too. So they have 6 to 10 all showing here. Then you have 11, 11 and 12. Okay, 11 to 14 rather, showing here. Or even 11, well, let's say 11 to 13. So one advantage and one disadvantage of greedy decoding compared with random sampling. Of course, the advantage is that it is fast. The disadvantage is that you can have redundant words, tokens generated. Then for 14 now, so you can have 14 and 15 here. You can see questions 14 and 15. So this one is asking, suppose probabilities are this. If top K sampling uses K equals 2. So for K equals 2, you just pick A and B alone. A and B are retained, the others are discarded. Then a model produces this now. If top P sampling is used, if top P sampling uses P equals 0.8, that means you add anyone that stops at 0.8, you stop there. So this is zero point 0.4, 0.65, 0.65, then point 0.83. Yeah, so that means that you just pick, say, A and B alone. Yeah, because you don't want anything above 0.8. So A and B will be left in this situation. Then of course you have the rest of the problems. So the other problem I'll be solving is solution number 15. Oh yeah, okay. Interestingly, yeah, I was explaining that. So we are going to solve this. A model produces all this, so we deal with this. All right, so let's go ahead and do that and see how we take that home. So let's start with problem 7. So you have problem 7. So problem 7, compute compute the softmax, the softmax probabilities for the logits 3, comma 2. And then give your answers, give your answers to 4 decimal places. Okay, so let's go for that. As a solution, of course, we have 3, 2 given. So these are the logits now. Logits are 3, 2. So first step, we compute the exponential, compute the exponential of each logit. So you have e raised to power 3, that is 20.0855. And you have e raised to power 2, that's e raised to power 3, e raised to power 2. So that is equal to 7.3891. Okay, so for step 2 then, step 2, you compute the sum. Compute the sum. So the sum is e raised to power 3 plus e raised to power 2, which is 20.0855 plus 7.3891, and that is equal to 27.4746. So with that in place, you go for step 3. So step 3, normalize each value. Normalize each value. So first token, for the first token, you have 20.0855 over 27.4746, and that is 0.7311, like that. Then second token, of course, first token is, this 20 over this. Then second token will be this over this now. So second token, so for the second token, then you have 7.3891 over 27.4746. That is 0.2689, like that. So final answer now. So for final answer, this is the kind of thing you have. You have your token, and you have the probability. Probability. So that's token. So you have token 1, which is 0.7311. You have token 2, that is 0.2689. So of course, the probabilities sum to you have 0.7311 plus 0.2689, and that will just sum to 1.000. So that's all we are required to do to compute the softmax probabilities, and that we have done. So that's how it goes. So if you're supposed to pick one of these normally, so you just pick token 1 because it has the higher probability. So that goes. We go for solution 15 then. Problem 15. So problem 15. So a model produces the following. Okay, let me even do it here. You have token, You have probability. So you have A, B, C, D. A, B, C, D, E. So probability 0.40, 0.25, 0.18, 0.10, and 0.07. Like this. Okay. So the question is, if top if top P sampling, if top P sampling uses P equals 0.80, which tokens are used? Which tokens, which tokens are retained? Okay. So that's top P sampling. So what do we do? Go for the solution. So first we have the token, we have the probability, and then we have the cumulative probability. Cumulative probability. So this now. So you have A, B, C, D, and E. Like this. So this is 0.40, this is 0.25, this is 0.18, this is 0.10, and this is 0.07. So cumulative probability now, see how that goes. So of course, this is A straight, that's 0.40. So next you have this, add this to it, and you have 0.65. Then you have 0.65 plus 0.18. So that would be 0.83. And 0.83 plus 0.10. So that will be 0.93. Then 0.93 plus 0.007, that will be 1.00. So, and the deal is we want to, so this is step one, right? This is step one right here, step one, right? So for step two now, step one is arrange probabilities from largest to smallest. Okay, I mean it's already arranged. So if it wasn't arranged, we would have had to do that. So step two now. So in step two, find the smallest set, find the smallest set whose whose cumulative probability, whose cumulative probability is at least 0.80. Okay. So from what we have already, right? So we see that A A the cumulative for A, as we saw, the cumulative for A is equal to 0.40. So that's what we have here. This. Then A plus B, you have the cumulative is 0.65. As we add 0.25 to that, you know, then we now go for the next one, A, B, and C. So you have A plus B plus C, and that results to the cumulative 0.83. Cumulative is 0.83. So we can then say since 0.83 is greater than or equal to 0.80, we stop here. We stop at C. We stop here. So then the final answer will be, so we have final answer, we have the retained tokens, retained, the retained tokens are A, B, and C. Then discarded tokens, the discarded tokens are D and E. D and E. So then we know that only the retained tokens, only the retained tokens are renormalized. They are renormalized. and used during during the sampling step. During the sampling step. And that's how that goes. So with that, we are done with this video on the computation, the calculation. Uh, every ChatGPT response starts the calculation. Every ChatGPT response starts with. So I'm going to flash the practice problems once again, and then to be all over for now. So you have 1 to 5, 1 to 5. Okay, say 1 to 4, even 1 to 4. Then you have 5 to 10. At least all of 5 to 10 can be seen here. 5 to 10. Then 11 and say 11 to 13. Yeah, 11 to 13. Then, okay, again, 11 to 13. 14, 14 and 15, showing 14 and 15, and then the rest. And then the rest. Let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not, why not go ahead and subscribe right away and hit the notification bell so you can always be alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges that you'll find out as you click. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.